In mathematics, groups and coding theory is a very important topic. So today we start with the some topics from groups and coding theory. Now the first unit is integers R. Now the next is congruence relation on a set of integers. If a and b are integers and n is a positive integer, then we say that a is congruent to b modulo n if n divides a minus b. See, a and b are any integer, so it may be positive, negative or 0 also. And n is a positive integer, that means n is a natural number. So whenever the natural number n is dividing a minus b, then in that case we say that a is congruent to b modulo n. And we write this as a is congruent to b modulo n. Now whenever a is not congruent to b modulo n, that means n is not dividing a minus b, then we write this as a is not congruent to b modulo n. And we say that a is incongruent to b modulo n. Now see this example. 16 is congruent to 11 modulo 5. Now comparing it with the standard notation, here a is 16, then b is 11 and n is equal to 5. So 16 minus 11 is 5 and his n equal to 5 divides 16 minus 11. So 16 is congruent to 11 modulo 5. Similar way 3 is congruent to minus 5 modulo 4 because 4 divides 3 minus minus 5, that is 8. But 17 is not congruent to 3 modulo 5 because 5 does not divide 17 minus 3, that is 14. Now see next theorem. If a, b, x belong to z, that means they are integers, n in n means n is a natural number and a congruent to b mod n, then a plus x is congruent to b plus x modulo n, and secondly ax is congruent to bx modulo n. Now the proof is very simple. We have to use just definition and concept of divisibility. Now, what is given to us? A is congruent to b modulo n. So, this part is common for both the proof. So, A is congruent to b modulo n. By definition, we can say that n divides a minus b. Now, from concept of divisibility, a minus b is equal to n into k for some integer k. Now, we call this equation as 1. Now, first result is a plus x congruent to b plus x modulo n. By definition of congruence, we have to show that n divides a plus x minus b plus x. So we start with a plus x minus b plus x. As there is negative sign outside the bracket, by changing the sign of every term we get it is a plus x minus b minus x. So cancelling x, it is just a minus b. But from equation 1, a minus b is n into k, where k is an integer. So finally we get a plus x minus b plus x is equal to nk. So again by using definition of divisibility, we get n divides a plus x minus b plus x. So by definition of congruence, we can write a plus x congruent to b plus x modulo n. So this is the proof of first part. Similarly, see the second part, x congruent to bx modulo n. It means we have to show n divides ax minus bx. So we start with ax minus bx. So again taking x common, this is x into a minus b, which is x into nk. So it is n multiplied by xk. Now as x is an integer, k is an integer, x into k is an integer. So by using definition of divisibility, we write n divides ax minus bx. Implies by definition of congruence, ax is congruent to bx modulo n. Now, one more theorem. If A, B, C, D belong to Z and n is in n, A congruent to B modulo n, C congruent to D modulo n, then A plus C is congruent to B plus D modulo n. Second, A minus C congruent to B minus D modulo n. And third, AC is congruent to BD modulo n. Again, the proof are on the similar lines. We are using just definition of congruence divisibility. Now, according to given information, here we can write n divides a minus b, and from this n divides c minus d. So using definition of divisibility, we get a minus b is nk and c minus d is equal to nl for some integers k and l. Now to prove this first part, we have to show n divides a plus c minus b plus d. So start with a plus c minus in bracket b plus d. Again changing the sign of b and d, it is a minus b plus c minus d. So from this equation, it is nk plus nl. So finally, it is n into k plus l. So by definition of divisibility, n divides a plus c minus b plus d, as k plus l is an integer. So by definition of congruence, a plus c is congruent to b plus d modulo n. Similar way, we can prove second part. The only thing is, instead of a plus c minus b plus d, we have to consider a minus c minus b minus d. Now see third part, AC is congruent to BD modulo n. So we have to show n divides AC minus BD. Now here the first step is very important. So you have to remember this step. Otherwise we can't do further. So AC minus BD is equal to AC minus BC plus BC minus BD. So here we are doing one adjustment, that we are subtracted BC and added BC. So from first two terms we can take C common, and from last two terms we can take B common. Why we are doing this part? Because we have the values of A minus B and C minus D. So using that values, it is C into NK plus B into NL. So again, by taking n common, it is n into ck plus bl, where ck plus bl is an integer. So by definition of divisibility, n divides ac minus bd. So by definition of congruence, ac is congruent to bd modulo n.